speak in any
Okay, we're recording.
Okay. Well, welcome everybody. Thank you for coming. Today we have the pleasure of welcoming one of our own, Dr. Professor, I guess I'm German. Professor Edgar Lobaton from Electrical Engineering. Professor Lobaton joined us this last fall, so it's a pleasure to have him here. He'll talk to us about some of his recent work when he was a fellow postdoc at UNC Chapel Hill in the Computer Science Department. Dr. Lobaton received his PhD from in electrical engineering from Berkeley, and he also completed his BS in electrical engineering as well as in mathematics. His research interests are pretty broad, including computer vision, sensor networks, robotics, and controls. And his interest in applications is also pretty broad, from spanning surveillance and medical applications and such. It's a pleasure to have him here. Thank you for coming.
Well, thank you very much, everyone, for coming, and thank you for the introduction. So yes, my name is Edgar Lobaton, and today I'll be talking about robust topological features for deformation invariant image matching. So let's see what that is about. So a little bit of motivation. So here I'm showing you an image. Pardon me?
No, we can't.
I don't think so. Okay. So a little bit of motivation. Here we have an image, and here I'm essentially showing you in a small region of the image that you can see over there in the small square that you observe. Now, for that particular image, what I'm going to do is I'm going to apply some sort of deformation. And this is essentially what you're going to see here. So I'm putting a grid as a reference. I'm applying the deformation to that particular image. And you can see how everything is essentially moving around. And then for that given image, we can look at an equivalent region that we have, and we may obtain something like what we see over there at the bottom right of the screen. Now, in those two cases, there's a certain number of points that we can call feature points that have been moved around. They have actually deformed. And one of our objectives is going to be able to identify which regions from one of the images correspond to the images or to the points on the other image. So that's a very general objective. And let's just think a little bit about the applications about these kind of scenarios that we have in here. For example, this in computer vision, this is a very common task when you're trying to do something like 3D reconstruction of any particular object. What you're given is two images, one corresponding to the right and the left eye. And they're looking at the same thing, but the thing may be actually deformed due to some change in perspective. You're looking at an object from a different point of view, essentially. Now, there's also cases, for instance, in which you may have a video sequence, and you may be observing something that corresponds to maybe something like a cloth that is actually deforming itself, or maybe a person that is actually moving around. A person is not really a rigid body. There are some actual deformations taking place. Or also, this could be related to maybe some medical applications, where we may have some sort of MRI of a person over time. Every month or so, for instance, you do some sort of MRI. Things are actually changing in terms of the physiology of that person. And we need to be able to register at that point what regions correspond to what regions in the brain, for example. And this could also be applied in between different subjects. So this could be a cross-sectional, essentially, study for some sort of medical application in that case. So essentially, those are the kinds of applications that we're interested in. And essentially, what we're looking is a way to register or figure out what point in an image corresponds to some other point in another image that we're given. OK. So given that we don't know anything about the deformation that is taking place, one of the things that we can do is that we can think about topology. So what is topology? Topology is often referred to as the rubber sheet geometry. So what that means, essentially, is that topology doesn't distinguish between spaces that have been deformed. It's often said that a mug of coffee, a cup, is essentially the same, topologically speaking, to a donut. So we're going to see essentially why they're the same. The reason why they're the same is because there's a nice transformation, a nice way of deforming one into another without necessarily breaking the object. So this is a little example showing you essentially how you can actually deform one object into the other. So they are both essentially equivalently in terms of topological, in terms of its topology. And what we're going to do in particular is we're going to look at some algebraic topological objects, which essentially gives us some sort of characterization of that space. And in particular, we're going to look into homology. And I'll go into that a little bit later. So the idea overall is that topology gives a characterization which is irrelevant, essentially, to what the space really looks like, as long as there's some sort of transformation in between them, some sort of deformation. Of course, that seems to be a little bit too broad, so we're going to try to, or we're going to have to actually improve or enhance those definitions. The classical definitions are given to us in terms of topological invariances and things like that. Okay, so to get started, we're going to start with something very simple. We're first going to consider what our image model is. So we're going to try to keep everything formal. We're going to assume that we're given two images, image number 1, 0 actually, and image 1. And they're going to be related by some sort of transformation. And that transformation essentially is going to be a deformation that's been applied between the two of them. So what do we have? An image is essentially a mapping from some domain that I'm calling omega to the reals for now. So I'm essentially just considering grayscale images, so black or white. And then we're going to consider essentially a relationship between the images corresponding to image 1 equals to image 0 composed with some deformation f, plus some sort of perturbation that has been added. Right? So what does this correspond to? F essentially is going to be, as I mentioned, this kind of deformation, which can be a change of perspective or some deformation happening over time. And P corresponds to some sort of error in terms of the measurements or some sort of noise that is added to the actual system. Okay, so and we're going to assume essentially some particular constraints for the perturbations and the deformations that we have. In particular, for the perturbation, we're going to assume that it's bounded. So the absolute value of the perturbation is going to be less or equal to some constant Kp. And we're going to have some lower and upper bounds also for the actual deformation. Now, what we have over here in this line is that we're saying that f of x minus f of x prime, the norm of that is going to be lower bounded by some function HL, lower bound function, of the norm between x and x prime. And same, we're going to have an upper bound essentially for that same difference between the function values. What that's telling us is that we cannot deform the image too much, right? If we allow it to deform, widely without any particular kind of bounds, then all that we're going to be able to do is essentially use the concepts from topology as they're usually stated. But by making these assumptions, we're actually going to be able to do a little bit more. Okay? And these are actually like very reasonable assumptions, because a lot of work actually assumes in some sense that if there's some sort of deformation, for instance, somebody running, there's a maximum speed, right? You're not moving at the speed of light, essentially. There's a maximum speed in terms of how fast things are actually happening. And that's what this is capturing. So what we're going to assume for the rest of the discussion now is that there's some sort of mapping, as I mentioned, between the images. That's f and some perturbation p. These are going to be completely unknown. We don't know what they are. But we're going to have some sort of bounds, and those are going to be known. Kp is going to be known. HL is going to be known. And HU is also going to be known. Okay? And those can be very simple bounds. It could be as simple as just putting essentially a constant times x minus x prime, essentially the norm of those two values. Okay, and our objective overall is going to be to, well, can you figure out essentially some sort of correspondence between the points in image 0 to the points of image 1 without necessarily having to solve for f or p? A lot of the work actually tries to solve for this f and p, and it can be very computationally intensive. And there may be too many parameters. So we're going to try to do it without necessarily knowing what f and p are. Okay, so let's be more precise in terms of the problems that we're going to try to solve. Problem number 1 is going to be the following. We're going to assume that we're given a point, x of 0, in image 0. And then we're going to be given a set of points in image 1. So that's what I'm calling lambda 1. And then based on that, what I want to be able to find is essentially, well, first of all, we're going to assume we know that there's going to be some mapping, which I'm calling f inverse for now. F actually goes in this direction, from image 1 to image 0. And f inverse is essentially the mapping onto the domain of image 1. And that's what we have over there. And what we're going to look for is we're going to look for the point x1, as you can observe over there, which is actually the one closest to f inverse of x0. So it's the closest corresponding matching point. Now, of course, if you were to assume that lambda 1, for instance, is every single point in the plane, then it would be essentially the point x1. f inverse of x0 would be essentially the point x1. But we're going to relax actually our problem even a little bit further, and we're going to assume that we don't have to test every single point. We're only testing a subset of them, and then we're going to be able to find essentially the closest one. So that's our objective at this point. We're also going to consider a second problem, which has to do actually with regions at this point. And we're going to consider that an overlap ratio or threshold that is given to us, which we're going to call tau, which is going to be between 0 and 1. And we're going to be given two neighborhoods, a ball around the point x of radius r0, and a ball around the point x prime with radius r1. And the ball at radius r0 is an image 0, and the other one is at image 1. Of course, we have the same mapping that we had before, f inverse. And at that point, what we have is that this ball that we have in here, this circle, this disk, actually maps to something that may not necessarily look like a disk anymore, right? If it was something like an affine transformation, this would be actually an ellipsoid. But in very general situations, that's not necessarily going to look like an ellipsoid. So it's going to look like something else. And what we're looking for is we're trying to quantify essentially the amount of overlap that there is between both of these different regions. And that's what is quantified by this particular ratio that I have over here, where we're taking the area, essentially, of f inverse of that ball intersected with a ball on image 1, and we divide that by the union of those two. So what happens if that ratio actually is equals to 1? It means that they have overlapped perfectly. If that ratio is 0, they're completely disjoint. And if there is anything in between, there is essentially a partial overlap between these regions, right? Yes?
Is x prime the point closest to f inverse x0?
Well, later we're going to make that connection, but at this point, the problem as it's stated is actually fairly general. I'm saying for any x prime that you give me, I want to figure out whether those two regions actually overlap or not. How much they overlap, actually. Okay? Okay. Yes, and please interrupt me if you have any questions. Okay, so those are the main two problems. So we're essentially trying to find what I'm going to call the closest matching point in here, and then we're going to try to figure out essentially the overlap between two different regions. Okay, so now how are we going to do that? And I mentioned essentially that one of the motivating factors is like there's a lot of very interesting concepts from algebraic topology that can be used to be able to characterize the spaces or sets in general, irrelevant of what kind of deformation is taking place. So what we're going to do is that first, let me introduce a little bit a couple of these concepts, in particular the concept of homology. And here, essentially, in a few words, this is what homology is. The kth homology of a particular set E, denoted H sub k of E, is an algebraic object that captures topological information about the set. So that's very general. But let's look at three given examples in here. We have a set E1, E2, E3, where the set is the actual white space, in these black regions in here. And here, let's consider, for instance, what's the rank. So that's essentially the dimensionality of this group structure that you can obtain, which is called H0 of E2. So just think of it in terms of like a number like that you're going to get. And this particular number that you're getting actually tells you, which is equals to 2, corresponds to how many connected components do you have in that particular set. And we observe that we have two sets in there. Also, you consider the rank of H1, E2, then that's actually going to give you 1 for this particular case. That corresponds to the fact that you have one hole in the system. So the idea is that we're going to use some of these concepts to be able to characterize essentially what these sets look like, and ideally what the functions are going to look like too, to be able to determine which regions actually correspond to each other. So that's the idea. And of course, I'm not going to go into too much detail in terms of how I'm computing this, but there's a lot of different methods for doing it. And if anybody's interested, I can take some questions a little bit later. Okay, so just to give one more example, for E3, for instance, you would have the rank of H0, will be how many connected components you have, again 2. But the rank of H1 of E3 in this particular case would be 0 because there's no cycles in that particular set. So that's what we're going to deal with. And actually for that, I'm going to show you one particular lemma that we proved. And the lemma is telling us the following. Assume that you have a sequence of 3 different sets, essentially E1, E2, E3, like the ones that you see in this particular slide. And there is an inclusion between them. So E1 is included in E2, and E2 is included in E3. And there is a map between them, which is the inclusion map, which I'm calling sigma sub ij. Right? So it's the inclusion between E1, EI, and EJ, essentially. For that, there is this relation in here, which is telling us something about the ranks of all these groups that I mentioned, this topological information that you're capturing. And one thing that I want you to notice, and anybody that's interested in the math, you can look at the paper, or you can ask me, of course, afterwards. But just a couple things to notice about this particular equation. One thing to notice is that this is essentially an inequality between rank conditions that you obtain. On the left side, we have a rank condition that only depends on E1 and E3. And on the right side, you have something that only depends on E2. What that means is that you can come up with a lower bound to the topological information containing E2 if you know a lower bound and an upper bound for the sets, which are E1 and E3. So for those of you that know some algebraic topology, this is essentially an example of persistence that is happening in here. So that's how you can derive all these things. Now, in general, if you were to actually, yes, question? The psi?
Star.
Oh, star, yes, yes. So that's essentially the lifted map from the actual sets to the homologies. So star means actually is the map
Induced.
between homologies of EI to homologies of EJ in that particular case. Okay, so what this is telling you actually, just to give you an example in terms of like intuition, if K was equals to 0, the number of connected components, what this would mean, this quantity here with the rank and the ratio of HK divided by the kernel, what that's telling you is essentially how many connected components are present in E3, in the set E3, that were also present in E1 in some way, right? So for this particular example, there are two connected components in E3, which are actually present also in some form in E1. So then that rank would be 2. And that would be that 2 has to be less or equals to the rank of H0 of EK, E2 in this particular case, which is again 2. So the equality actually holds for this particular case. So that's just one very simple example. Okay, so now how are we going to do the characterization? Well, here we notice that we need sets. Now somehow we need to obtain sets from our functions. So again, remember that I said that an image is really a function. So we have like the grayscale value essentially, which is the height for that particular function. And I'm showing you an example here. What I'm going to do is I'm going to take essentially slices. So I'm going to take a lower slice and an upper slice, and I'm going to consider everything in between those two planes. And that's how I'm going to obtain sets, like the ones that you see here in the diagram. So anything essentially between the lower plane and the upper plane, is going to be essentially that set that I'm interested in. And that is called actually an interlevel set at that point. So the values A and B are essentially the lower plane value and the upper plane value. And for that, I'm actually going to define 3 particular sets that I can obtain for any given A and B. I can define E0 minus, which is going to be taken from image 0, right? One of the images that I have. It's the inverse of that particular set, so anything between those two planes. Then E1, which is going to be similar, but taken now from image 1. And then we're going to have E0 plus, which is going to be similar as before, but it's going to contain essentially a different interval at that point. Now notice that E0 minus is actually the interval is actually smaller than the interval from E0 plus. So right away you know that E0 minus has to be included in E0 plus. Right? But furthermore, actually, what you have is that E0 minus has to be contained in F of E1, which is contained in E0 minus. Essentially, you're sandwiching these particular sets that you have. So you get essentially the inclusion that you required initially. And just to remind you of this particular constant, that Kp corresponds to the amount of perturbation that you're adding to your function. So it's essentially the upper bound that you had for the noise or error measurements that you had. Now, given that, we're going to use the same lemma that we had before, in which we had some sort of rank condition between E0 minus and E0 plus, and that's this condition over here. And it's going to be less or equals to the rank corresponding to F E1. Now, the one thing to notice, and this is why we're using topological invariances, is that the homology for F E1 is going to be the same as the homology for E1. And that's essentially because all these invariances are irrelevant on what kind of deformation you're applying, right? So then this F is the same as having the F or not having the F. So what this tells us is that this is giving us essentially some sort of relationship to be checked between the homologies on image 1 and the homologies of image 0 without finding the map between them. So at a very high level, what we have so far is that if you give me 2 images, I can compute a lot of these different conditions for all different intervals A, B, and then I can obtain a lot of these ranks too from images I0, sorry. And then if these 2 images somehow are deformed one corresponds to the other based on some sort of deformation, then what you obtain is that this rank condition had to be satisfied for all of them, for every A and every B. Now, if there's one violation for one of these A or B, then definitely these two images are not related by some sort of deformation. Right? Okay, so that's great. We have an idea to recognize or identify essentially images. But of course, there's no localization information. That's telling you need to take the entire image and make sure that you compare it to the entire image. So how do you figure out whether the small region here corresponds to that other region somewhere else? Well, that's what we need to do next, essentially. OK, so in this particular case, essentially, now we're going to try to localize the same invariances that we used before. Now, instead of having just A, B, now we're also going to add an R. So that's going to be a radius for some particular ball that we're going to consider around some point. And the idea is that we're going to define the same thing that we had before, E0 minus, but now we're going to intersect it with some particular ball centered at some point X. And it's going to have a radius corresponding to HLR. And I'm going to say essentially why HLR in a second. Same, we're going to define a new E1R. It's going to be E1 intersected with a ball at some point X of radius R. And similarly, we have an E0 plus. And for this particular case, what we're going to have is, again, the inclusion that we actually want. We have E0 minus is going to be included on F of E1. Now, E1 is going to be centered, essentially, around the point F inverse of X. Right? So that's the actual matching point after you have that. And then that is going to be included in E0 plus X. Now, what's happening in terms of these sets? Essentially, we already had inclusion between all the different E's in here from the previous slide. But now what we would require to be able to have this to be valid, this inclusion, is that we need essentially some sort of inclusion between all these three balls. And that can be seen essentially from the diagram that you see over here right now. This ball centered at X with a radius HLR is essentially a very shrink version of the ball that you may start with of radius R. So that's a small ball. And then the HUR, the ball with radius HUR, is actually a blown up ball. And what we're saying in terms of the inclusion, the final result that we have, is that if we take actually a ball in image 1 of radius R, and then we map it using F inverse, or F actually, what we are going to obtain is that that new set that you get after you map it back is not necessarily a ball again, but it has to be contained between the small ball and the larger ball, between those two. So that's why we have essentially like this inclusion. And that essentially is because we have this model in terms of like how much deformation we're going to allow between things. OK. And hence, we're going to have a similar result to the one that we have. Now, note the one problem here is that we got rid of F, the outer F in the inclusion, essentially, because when we're taking the homologies, that deformation doesn't really matter. But we still have the F inverse of X0, which is telling us that these conditions in terms of the ranks are equivalent for a point X0 and its corresponding matching point F inverse of X0, which is in image 1. Right? So these are, again, conditions that you can do or you can use to actually check whether a region matches to another region. And that's great. Now, essentially, this is the result that we're looking for, except a couple of things. Thing number one is that to be able to verify that this is going to be the case, or to be able to find, for instance, given a point X0, a corresponding matching point F inverse of X0, we need to search the entire image. Right? So that's a lot of computation for that case. And that's why, essentially, like originally, the original problem required, OK, let's consider a subset of the entire image domain, and let's call that subset lambda 1. So in that particular case, actually, to be able to account for that particular modification in our problem and our definition, there's something very simple that can be done in here. And essentially, that corresponds to, instead of considering balls of radius HL of R, or HU of R, you need to add an extra term here, which accounts for how far away points are with respect of each other. And I'm not going to go into much detail, but if you're interested, I can point you to the paper where essentially we make those derivations. But there's a slight modification that will take into account essentially the fact that we don't want to check everywhere, but we only want to check on a subset of them. Right? OK, so we have that particular result. Now, there's also essentially one other problem with this particular derivation, and it has nothing to do with the theory. Essentially, we have solved our problem. It has to do with the actual practical applications of this for this particular theory is that we're actually going to use them not in continuous images, but we're going to use them in discrete images, right? So the images are actually being sampled. So when we try to compute some of these quantities in terms of the homologies and everything else, one little mistake in terms of like where you're sampling your set, and you're going to end up with something completely wrong. So that's a very big problem, and that's a very big problem for anybody trying to do something with some of these algebraic topological concepts. Actually, like I'm going to have to refer you again to the paper for that particular problem, but the solution for that is that instead of using these original images, image 0 and image 1, what you do is you actually build a new filtration that takes into account essentially some sort of filtering of your images. You could, for instance, do some sort of Gaussian smoothing. That's one thing that you can do. In my case, what I did is actually I took essentially some morphological operations, and that guaranteed me pretty much that whatever solution I have, like, it's going to be robust to these kind of sampling issues due to discretization of an image. Okay. So that being aside, essentially that's what we have right now. Okay, so coming back to this particular result. So this particular result tells us that, again, it gives us a way to identify whether a point x0 and some other point x1 correspond to each other by checking that all of these different conditions in terms of the ranks of the homology are going to be satisfied. Of course, this depends on what? Radius A or radius R and some particular constants, I guess, for an interval A and B. So those are the values that we need to specify. So we can try multiple combinations of these things and then get several descriptors for this particular inequality. And then use that to be able to verify whether a region matches or it doesn't match. Right? And as long as there is one of these conditions that is not satisfied for some A, B, and R, then what we're going to obtain at that point is that those two regions don't match for sure. Okay, so, but this tells us something about in terms of like how far away things are with respect to a point x0, but it doesn't tell you anything about orientation, right? So something can be very far or very close, within your particular range, but what can happen is that the orientation could be completely messed up, so like that particular representation that we had over there doesn't take that into account at all. So the next thing that we can do is that we can actually build on top of this, as long as everything, like is satisfied in terms of our condition, we can build something on top of that that gives us some information in terms of orientation. And that's essentially what I'm doing here. And for that, I'm going to build what I'm calling a topological template. And some people, actually, other people in feature kind of matching applications have done similar things. But what we're doing here is actually a little bit more robust because the theorem needs to be satisfied. The conditions for the theorems need to be satisfied in order to guarantee that we're going to have actually the right matching. So we need to be a little bit careful, and there's some things to worry about. I'm not going to go, again, into too much detail for that. But essentially, this is what we're building. So this was the original point x0, essentially right in the middle of this particular template. And we were considering disks around it to figure out essentially, for different R, whether we have the given rank conditions that we're interested in. But instead of just considering that particular point, we're also going to consider other points around it. And for each one of these points, essentially, we're going to also consider small R's in between. Now, what we're going to do is that we're going to take this entire thing, which is telling us that at a given location there's some rank conditions, and for neighboring guys there's also going to be some rank conditions, and we're going to call this our topological template, right? And then for the other image, or in image 1, we're going to have a similar template, but it needs to account in terms of the unknown deformations that are going to be applied. It needs to be accounted into that too. So that's also built in, and we can do it essentially by modifying all these radii kind of bounds that I gave before. So that's extra results, I guess, that come a little bit later. Well, you can look up, I guess, in the paper. Okay, so essentially, based on that, what we have is a solution to our initial problem. And the solution is very simple. All that we need to do is that we need to compute all these rank conditions that we had before in terms of homologies. And then we need to check between the rank conditions for a template around one given point x0 and a template around every single test point that we have in image 1. And once those conditions are satisfied, we're going to call essentially that our matching point. Of course, there could be more than one, but we're going to try to, we're going to see how well we perform essentially, and I'm going to show you some results for that. So that's the basic idea for problem number 1. We just go through, compare all the different ranks, and if any conditions are not satisfied, then that point is definitely not a matching point, and then we move on, and we're going to end up with a subset of them. Now, for the problem number 2, which had to do essentially with how much overlap there is between these regions, we're going to be able to apply something very similar to this. Actually, the first thing that we're going to do is that we're going to find essentially this closest matching point. And based on this closest matching point, what we can do is that we can figure out essentially a lower and upper bound for the overlap that we have between regions. So that tells us that once we solve this problem, we can actually come up with an estimate for what would be a good, or what's the ratio of overlap between the different regions. So you just give me any region in here and some other region in the other image, and then you're going to be able to come up with an estimate by doing this as well. OK, so that's essentially main things that we have here. And now I'll show you pretty pictures. Hopefully they're pretty. They're pretty to me. But, OK, so this is essentially some results that I pre-recorded. So this is not real time. The display has been done in real time. But actually, my bad. Let me try a different one first. OK. So hopefully you can somewhat tell the difference. So we have two images, image 0 and image 1. So image 1, of course, is the deformed image version that we have over here. And what I'm doing is this is actually a very interactive demo, and I'm going to go over a couple of points here so you can see how the algorithm actually performs. I'm selecting a point, and that small ball is essentially the maximum radius that I'm considering. So I'm considering small little circles around, smaller than the one that I'm showing you in there on image 0. And then on image right, I already selected a bunch of points. Those are my test points, the lambda one. And then I'm checking all these rank conditions. And I'm coming up with a subset of them. So the blue and red points are the points that I obtain after checking all these rank conditions without using the template. So that's just purely looking at distances essentially between things. Now the red points are a subset of both of them, and those red sets are essentially the points that I get after I consider the template information, the template model, which is a little bit more expensive, of course, but you're testing it also in a subset of them at that point. So you can see that the blue ones, reduces the entire image by a lot, so you don't have to search over the entire image, but now you end up with a very few set of points. And the red one, is essentially in this particular case, for instance, it has really narrowed down essentially what you want to get at that point, which is essentially the eye of this picture. By the way, this image is a very standard, I guess, image that is used in computer vision. It's a graffiti image. It's just some guy, I guess, killing a chicken. Not that I want to kill chickens or anything, but that's just what they use. Not yes. OK. So here's another example here, too. For instance, I'm picking a point here, and you can see that there's a subset of blue points, but you actually pick up the right one when you do essentially the template matching component. And I'm just going to select a couple of them so you can see essentially where there is some sort of ambiguity. Remember that I'm only considering that the small regions. And in this particular case, two different regions were selected. One region over here by the ear, which is the right one. And then the other region, which is close to what I assume is the knife, right over there. And actually, if you try to look at that small region, they look pretty much the same at that point. So it's very hard, even for anybody just looking at those small regions, to identify what the difference is. And for instance, there is catching the eye very easily. Now there's a little bit more ambiguity in this particular region over here. Let's go a little bit more towards the chicken. It found in this particular case the right location of the chicken in between the eyes. And let's see something that is maybe going to fail a little bit more. So in that particular case, instead, it actually found somewhat of a long region. And essentially, it's like everything in that region essentially looks a lot like what you started with. Maybe some other region would be something like that, close to these numbers that we obtain over here. There's also a lot of ambiguity there, too. And maybe one or two more things. Okay. And this is a location essentially close to the leg of the chicken, and it's actually finding the right location there. Something else close to the leg. OK. So actually, if anybody has any suggestions about where to test it, I can.
I have a question about the real-time duration of that computation. How long did it really take for it to find those red spots?
Right. So right now, so disclaimer, first of all. So the computations that we have, because essentially we're taking all these different regions and computing homologies and things like that, is very easily to be parallelized. So this could be essentially stupidly parallelizable for this particular kind of application. So that's something that we're looking into maybe for a little bit later. Some student that wants to do this in CUDA or something like that, to be able to parallelize all that. Okay. Once I said that, okay, so you can optimize algorithms and everything else. But essentially, this image is about 800 by 800 pixels. And I'm taking a subset of points that are about 3 pixels away from each other. So not every pixel, but every third pixel, and then same in terms of rows. And for that, it's about for a single image to be processed, because essentially the expensive thing is to figure out all these homology rank conditions. It's taking about 2 hours to do one image. And then same for the other image. The comparison is actually very quick, so you don't have to, that takes a couple of seconds only at this point. But that's essentially how long it's taking right now.
So in the computations here, are you assuming you know KP?
Yes, so I give a bound for KP, and actually what we did in terms of like the results is that we applied the deformation for which we can figure out what KP is, and we changed the range of values from like 0 deformation to like, I don't know, what I'm going to say is 100, right? And what I guess essentially in terms of the actual KP is going to be somewhere in between. I actually chose something close to 50 essentially in between. And you're going to see actually the performance of the algorithm, like based on like the different values, I guess, as you apply different deformations and you're above what you estimated or below what you estimated. I mean, it's not that all of the time doesn't work. It just doesn't work for every single point.
So in practice, if you don't know what KP is, then would you suggest a good way to be that try for different values of KP and look for persistence in?
Right. So like there's many things that you can do. And essentially, like one of the things that you can do is that if you are observing, it really depends on the application, right? If this is, for instance, some video sequence that you're trying to analyze, as long as you have an idea what the maximum velocity is and how far away the targets are, then you're going to have an idea of how much things are going to change in your image, for instance. You can also like figure out essentially based on some person that's going to be an expert that is going to be selecting points from one image to the other image, like learn essentially what's the distribution of these things and account for 95% of, all these different motions. So that's going to be your upper bound at that point. So you know that worst case scenario, you're going to do 5% wrong essentially at that point. So you can also do that too. And another thing which is going to be actually an extension for our case is that while maybe you don't know it's necessarily exactly what that threshold is, but you may learn a little bit of a distribution at that point. So once you learn the distribution, how can you take that into account? So that will be a probabilistic extension that we're working on too.
Is it possible that for a certain R, find 2 regions that are topologically consistent, but geometrically inconsistent?
What do you mean by geometrically?
In other words, actually they match only topologically over a small area, but when you look at the thing in its context.
Right. So there's not an actual F.
Right. The geometry is completely different.
Right. So there's a couple of things. So for instance, in the case when I wasn't considering the orientation template, right, like mirrors of a given region are equivalent because everything is in terms of distance. So there's invariances or ambiguities in terms of like that, for instance. Also, even in the case of the template, there's still a lot of ambiguity because you're still discretizing essentially the space. So, but we didn't notice that happening in real time for images that often. So it's not necessarily a proof that this is the only region that actually matches. It's just that you're really trying to get rid of as much of things that don't match essentially as possible at that point. And that's a guarantee that you have for this case. But I mean, there's still like we're still working on extensions for which you may have some sort of guarantees that there is definitely going to exist some perturbation and deformation that explains, in that case, what you're observing. That the matching, it can happen. So, future work, I guess. Okay. Okay. Any other questions or any suggestions about where to click? Actually, one region I guess that I wanted to select maybe is, for instance, that region. I'm selecting a gray region right in the middle, right next to the graffiti guy. And in that particular case, you get a lot of small regions, right? Like regions over here, up there, all over the place. And that's because there's a lot of ambiguity in this particular case. Okay. So let me show you actually one more. One more simulation that I have in here. Okay, so out of all these different points, essentially, like I have found, like for every single point, more or less, in one image, I can match it to the other image. And by the way, when I gave those time estimates, this is not the time estimated for one point to match against the entire image is the time to estimate the entire image against the entire image. So I have a map essentially between one image to the other. And for that, for instance, from there I can select, for some of these regions I'm going to have a large regions. For some of them I'm going to have a smaller region. So I can select regions that have a smaller matching section, I guess, set on the other, on image one, and which corresponds to having a very accurate, essentially, like a precise idea on where it's actually corresponding to. And here I'm going to show you a couple of examples in here. So for instance, I know very well that this point over here matches to that point over there, and actually, I mean, it's the right match. And I think every single one of the ones that you're going to see here, actually, they're the right matches. And for some of them, you can see actually a lot of deformation happening in there. And some of them, there's actually a lot of them that look a lot alike. For instance, that one actually has a lot of deformation taking place in that region. It actually somehow finds that that region is the same as that one. I think there's a lot of deformation too. Regions like the eyes and things like that. And of course, I'm choosing a threshold when I'm doing that, so you can get more regions if you choose a lower threshold. Just to show you a couple. Something over here. Something over there. Some more there. And in a couple more, you'll see pretty much all of them together. And these are actually all right in this case. Okay, so that's essentially all the points that were found from one image to the other image. Okay. So let's go back to the presentation, actually. Okay. So
this is very important for mosaic.
Right.
This type of
yes. That's another application. Okay, so in terms of the results, so I showed you essentially what the algorithm does, like what it looks like, but I'm going to quantify now the actual measurements, and so we can actually compare them to other algorithms or other schemes to do the matching. And again, what we're obtaining is essentially for a given region and matching it to another region over there. And the way how I'm going to actually quantify measurements are going to be by using the methodology suggested by problem number 2. So I'm going to try to figure out essentially how much overlap there is between two regions. So I'm going to assume that at the center of this region there is a small ball, and I'm going to try to figure out how much overlap there is between those two. My method, for instance, every time that it finds a match, it's going to say there's an actual good overlap, and I can actually quantify how much overlap there is, or at the very least come up with a lower and upper bound. And then in real life, as a ground truth, what I know is that I know exactly what the map is from here to here, so I can actually find that F inverse of the ball, center at point X, and then I can figure out how much is the actual overlap. So based on that, I'm going to have a bunch of points here, and then a bunch of points over here. So I could select them randomly, but what I'm going to do is I'm going to pick a uniform grid. I think we had over 10,000 points essentially for our simulation. And then at that point, you're going to obtain these measurements of recall and precision. And for the recall, what you're measuring is the number of correct matches. So the number of times that you said, like, oh, there's a match from here to here, and there was a real match, right? And divided by the total true matches. So the total number of matches there is if you actually know what F is, right? So like, that's our ground truth. And then we're going to, so what is that measuring essentially is, how many times essentially did you actually get the right matches that you have in here? Now notice that if somehow, for any given point, I tell you the entire image matches, right? Then you're going to definitely get the right one at some point. So that ratio is going to be 1, right? So you can get 1, by doing something very silly in your algorithm. However, that's why you have precision as well. And precision tells you that that's a ratio between the number of correct matches divided by the total number of total detections. So you have like 100,000 detections for every single point that you match, then you're going to have a very low precision. So you want very high precision and you want very high recall. So that's what you're going for. This is an example of another image that was actually used for our analysis that corresponds to a boat that was deformed, the image of a boat. And I think you're going to see it a little bit later as well. Okay, so that's a little bit better, clear version of the boat. So we start with this image, and after deformation, essentially we look like something that it looks like that. And these are essentially our results. Okay, so first column, the graffiti image with the chicken. And second column is the boat image, like the one that you have over there on the right. Now, notice that what I'm plotting here is precision or recall on the y-axis. On the x-axis, I don't really know why, but traditionally we plot 1 minus precision instead of precision itself. So where I want to be, instead of being 1, 1, I want to be at 0, 1, somewhere up here. That's doing the best that you can actually do at that point. And essentially, these are the different plots that you see. Like the red and the blue corresponds to descriptors and matching algorithms like SIFT and GLOSH. And then the green one is our algorithm, essentially. And you see that essentially you get very good performance every single time. So I'm not telling you how I'm quantifying deformations, but essentially I'm applying a 30% deformation here. And in that case, I'm getting pretty close to 0.95 recall. And remember that essentially all the algorithms that we develop, essentially, they guarantee that you're going to find essentially like the right match. But you may end up with a big set of them, right? Essentially with a cover for that. So you're going to have a very good recall, and then depending on how complex your testing is, how many of these homologies you're going to be testing, then you're going to be able to narrow down that set to get something very small and precise, and that's why you can actually improve the precision at that point. But in all of these cases, this is 30% deformation, 30% deformation plus some noise, and the noise was essentially plus minus 10, uniform between plus minus 10. And then a 40% deformation, you are essentially outperforming SIFT and GLOSH, which is essentially what everyone is using nowadays. Okay, let me give you another example, and this is actually some results from another data set. And this data set is actually a little bit more complex, and this is actually more like what people usually use. What we're doing here is we're actually getting, what is called like a homography deformation, essentially, of an image. And that corresponds to, for instance, taking a picture of an object at a given viewpoint, and then changing your viewpoint and taking another image. Right? So it's not any deformation that is going to happen, but it's essentially an affine transformation that is going to happen at that point. And that's essentially what you observe over here. So we have the first image, our original image, and then some sort of deformation because we changed the perspective of the camera. And that's what we're doing. Now, in this case, you select regions of about the same size. That's not going to help too much because there's a lot of scale changes. So these regions need to be here larger than over here. Of course, we don't want to pre-select those regions for our program because that's completely unfair, right? So instead, what we did is that we used actually what is called a Harris affine region detector, which just finds region of interest in this image. So it pre-selected a bunch of different regions in here, and it pre-selected a lot of regions over here. Those regions are not necessarily matching regions. They're just regions that look interesting. There's enough change. And then we use those regions to be able to determine, using the same rank conditions that we had before, to be able to determine whether there is a match or there is not a match in our case. And essentially, these are the plots that we obtain in this particular case. We still, actually, in some cases, we're actually really, really close to our chain, I guess, the desirable outcome, I guess, 100% precision and 100% recall. But of course, once you start having much larger, essentially, changes on perspective of about 30 degrees, then you start performing pretty much just as well as SIFT and these other descriptors. And one thing that we notice is that essentially this pre-selection using the affine region detector, this Harris affine region detector, in some sense, all of these SIFT and GLOSH algorithms are designed to take into account the fact that everything that you're doing is essentially like an affine transformation. So it's kind of like giving them an unfair, I guess, advantage. So we do feel a little bit like we're in a disadvantage, but we didn't have anything better to do. So at least for now, maybe in the journal version, I guess it'll be a different version, different idea, I guess. But yeah, essentially that. Okay, so, and just because I did mention essentially that we are building essentially topological graphs with attributes, let me just mention a little bit about that. The idea is that we have these templates. These templates can be compared one to another by just a simple inequality constraint. But what we can do is that we can take several of these regions that we have over here, and I'm just drawing or denoting those regions by a black or red dot. And then for each one of these regions, we're going to have these templates with a lot of rank conditions between them. And in between those regions, we're going to have a distance, and we have a lower and an upper bound for the distance, using our model on the deformation. So essentially, we can put all of this information into a graph where each node is going to have all these rank conditions that we computed around a region. And in between the nodes, the edges are going to have weights, essentially, or some sort of attribute corresponding to the bounds, upper and lower bounds for each one of the distances that we have. And in that way, we can actually select a region, a graph, essentially build a graph out of this. And something that we can do, which we haven't done actually yet, and it's again future work, is that if we start building a graph on image 1 and we build another graph on image 0, we can look for essentially the largest subgraph for which we get an isomorphism from one side to the other side. And essentially that corresponds to finding the largest connected component in here that matches to the other image, right? So you're not just matching a single point. Now we're going to match essentially an entire region of the image from one side to the other. So it's still like some of these things are still work in progress. Okay, so just to mention a little bit about how to generalize the idea and how else can we actually apply a lot of these concepts, let me describe in a few words, in a very abstract sense, what the methodology was here. So the general idea is the following. So we take into account, or our input essentially is a function over some space. In this case, it was the image plane, and we had some function which was the color. Also, we had as input some sort of bounds on the deformation and perturbations, right? So deformations because there was some sort of change in perspective or motion due to whatever object that we see, and perturbation because there was some sort of noise in the measurements or uncertainty or quantization due to discretization of the image itself, of the function. Now, what was our output? Our output was actually a characterization of the function which was invariant to the deformations and perturbations that we defined within our bounds. Okay? So that was essentially our main output. Somehow we characterized it. But also we had essentially a matching process using the rank conditions through which we can have a direct estimation essentially of what regions matches to the other regions without specifying any sort of, without estimating actually directly what the actual deformation was. I mean, we never estimated really what f was. And also we didn't specify a given metric at any point. This was just, do they match or they don't match? Yes or no kind of answer. Of course, you can quantify everything else in terms of performance, but there was no actual metric that we had to define, which is kind of important because in many cases, many applications, choosing a metric is a very, very hard problem. You don't necessarily know what the right metric is. Here we said, you don't necessarily need to, as long as you have some sort of bound. Okay, so what kind of extensions can you have? And this is actually, in terms of my broad area of interest, I guess, random things that I like to do. Well, one of the things is definitely extend this in terms of a probabilistic method of the algorithm. The next one is that we can actually apply a lot of these concepts to sensor networks and robotic swarm kind of applications. And just to give you an idea, let us consider a bunch of sensors, agents, for instance. Each one of the black dots corresponds to an agent that you may have. And the blue regions corresponds to some sort of sensing coverage that you may have for the particular application. It could be a camera that you have, some motion sensors, some temperature sensors, something like that. You're making some sort of readings based on that, so you're making measurements. And then what may happen is that, well, maybe these things are moving around, and they may be moving around because either you have some sort of control over them, or maybe they're moving around because they're in the ocean and they're floating around. So what happens in this case is that there may be a lot of uncertainty. If you are, for instance, in somewhere where you have very accurate GPS, then there's no uncertainty. But if you are, for instance, underground or indoors or underwater, then you're not going to have, GPS accurate localization. So you may have all these different sensors with measurements that you have, and a lot of uncertainty in terms of like where those sensors were. And for those kind of cases, you can also essentially those are the deformation components of the analysis that I talked about, right? The actual localization of the sensors is essentially some perturbation that you can apply in terms of localization, and also there's errors in the measurements, so that will be the other component. So you can try to characterize essentially the configuration and the measurements that you have for this particular system using similar techniques, and that's of course an extension of future work. And just actually to conclude, so one of the things that we had in here is that we built a robust localized topological descriptors that are built to characterize neighborhoods of images. And of course, this was done by computing all these different rank conditions. And then everything was tested in terms of just simple inequalities, right? So there was a lot of work. I mentioned that some of these algorithms take a little bit of time, but they're doing very dumb computations that can be parallelized very quickly. Right? Yeah, and just to conclude, I would like to thank essentially our sponsors, NSF primarily through a bunch of different grants. And I'll take any extra questions that you may have. Thank you very much.
Any questions? Yes, Jennifer.
When you're calculating all of these ranks of the homology groups,
Speak up, Jennifer.
when you're calculating the ranks of the homology groups locally, you have your grayscale values, right? And so you have this level sets based on your grayscale values. So do you end up with just like one homology descriptor, or do you have like a filtration?
Right, so essentially, so the question was, for the different values that I have essentially in the interval A and B, when I'm computing all the homologies and I'm getting all these sets, do I end up with a single rank condition that describes everything, or do I end up with like a sequence of them in some sense? And right now, the way how this is implemented, you actually end up with like a bunch of them, so you can put everything into a gigantic vector with all these different ranks for the different A and Bs and Rs that you're choosing. So it's a gigantic descriptor. Most of them actually are going to be 0. And the reason why they're going to be 0 is because there's nothing interesting happening a lot of the time. There's only certain intervals that are very interesting. Actually, one thing that you can do to generalize that, so you don't have to be doing all the different A, B intervals, is that you can essentially take advantage of the persistent diagrams. And by doing that, you can actually compute essentially for every single A and B, like what you're going to get, characterize the entire filtration, as you mentioned. So that can be done. That wasn't done in here because we were lazy, I guess, and we tried the simplest thing that we could. But it's one way in which you can actually speed up this process and actually get a better performance too. And something that we are considering for later on too.
So this method would work very well if the image if the image has a lot of features, right? For example, if there's huge patches of same texture, then there'll be a lot of ambiguity in matching. Is that correct?
Yes, that's right. And actually, so the question was essentially like this required that for these regions or for these images, there's a lot of variations, a lot of interesting features. But what happens when you have a lot of like homogeneous regions? Well, in that case, like even a person can't do anything about that. Essentially, you're not going to be able to match it accurately at that point. But the good thing is that you're not going to match wrongly. Essentially, you're just going to get a large set that tells you that the right solution is somewhere in this large set, which you could still apply or use in some sort of algorithm to refine it. Actually, you can actually use if you build a graph, and there's more constraints at that point, so you can actually use even that information for those cases. The other thing that I mentioned is that this subset of points, the lambda 1, that you can pick to be able to narrow down essentially your detections, or you can use it to narrow down your detections. So you can start with a very coarse grid of points, do like a few tests for those, remove everything that you know for sure is not interesting, and then start like putting more samples in regions that you think are interesting, where there may be a match. So you can do this in a hierarchical way, and then improve essentially performance and speed by doing that as well too. So future work. That's good. Yes.
Yes, Jennifer.
In terms of changes in like grayscale values or like added noise, is that just all contained in your perturbations?
Yes, so the perturbations are meant to mainly account for errors in the sampling or some noise that may have something like a mean 0 kind of attribute. But for things like grayscale shifts of the entire thing, like somebody turns on the light, for instance, at that point, the whole thing like gets brighter. That's not taking into account that. And there's actually the journal version that we're going to be presenting. We're going to generalize this method to account for that without sacrificing much of the computational complexity.
It's a very pragmatic question. When you talked about speeding up the processing, but you won't use MATLAB for that.
Definitely not. Actually, to tell you the truth, we're not using MATLAB right now. Like, well, I'm using it only for display purposes, but I'm writing everthing in C.
Yeah, I was wondering how you're going to speed up an interpreted language, right?
Right, I tried that at some point, and it was not pretty. It'll take days, I guess, to find something.
Any other questions? I have one more question.
Sure.
The slide before that. How many bottles of whiskey would it take a sailor to see the second mechanism?
Well, our algorithm is not too that complex, I guess. We haven't made that comparison yet. Maybe next time.
Speaker again.
Thank you.